Let me welcome you to this lecture. We have now learned about the character table and what information are available within the character table, as well as we have learned how to obtain this information for any particular point group, and then we can construct the character table for any particular point group. So during this process we have also learned how to find out the symmetry of the rotational modes as well as the translational modes of a molecule, but we need to work out how to find out the symmetry of the vibrational modes, and that's what we are going to do during this lecture. So as we know that there are 3n degrees of freedom in a molecule, and out of these 3n degrees of freedom there are 3 translational modes and 3 rotational modes, and then we are left with 3n minus 6 vibrational modes in a particular molecule. So this is going to be 3n minus 5 for linear molecules, as they have one less translational mode. So let us now find out, or let us illustrate how to find out the symmetry of the vibrational modes in a particular molecule by taking the water molecule as the example. And we know that the water molecule has the C2B point group. So let us write the C2B character table first. There are 4 irreducible representations: A1, A2, B1 and B2, and the characters then the symmetry of the translational modes as well as the symmetry of the rotational modes. We found out that translation along Z has A1 symmetry, while translation along X has B1 symmetry, and translation along Y has B2 symmetry. Similarly, rotation along Z has A2 symmetry, rotation along X has B2 symmetry, and rotation along Y with respect to y-axis has B1 symmetry. Then Z square or the Z square orbital transforms as A1, the XY orbital transforms as A2, and the XZ and YZ orbitals transform as B1 and B2 irreducible representation respectively. So this is what is the character table of C2B point group. Now if we want to find out the symmetry of different vibrational modes in water, so what we know here is that there are 3 atoms in this water molecule, and there are total 9 degrees of freedom. That is 3 into 3 is equal to 9, and out of these 9 degrees of freedom, if we do 3n minus 6, then we get answer equal to 3. So water molecule has 3 vibrational modes of symmetry, and during this lecture we will figure out, or we will work out the symmetry of these vibrational modes, or else what we can say is that we will find out which these vibrational modes belong to which particular form basis for which irreducible representation in C2B point group. So before to begin this, actually we need to find out the reducible representation by taking the 3n degrees of freedom as the basis. So let us find out gamma 3n for water molecule, and if we do so, that because there are 3 atoms in water molecule, and if we take Cartesian coordinate on each of the atom as the basis, Then there are total 9 vectors, and the character of identity operation is going to be equal to 9. Then if we do C2, we see that the two hydrogen atoms change position, and that is why the they do not contribute, or vectors on these hydrogen atoms do not contribute towards the character, and only vectors that are present on the oxygen atom are going to contribute towards the character. So when we do C2 operation, x goes to minus x, similarly y goes to minus y, while z remains along z itself. So minus 1 from x, minus 1 from y, and plus 1 from z. So total character of the matrix is going to be equal to minus 1. When we do sigma v x z, none of these atoms change position. So all three atoms in water molecule are going to contribute towards the character, or vectors on each of these atoms are going to contribute towards the character. So we can figure out the character for one atom, and then sum it up for all the three atoms, and to find out the total character of the entire matrix, that is the 9 by 9 matrix. So if we do it for the oxygen atom, that is sigma v x z, and because the sigma v x z plane, when we do reflection on the sigma v x z plane, x axis will not change direction, as well as z axis will also not change direction, while y will go to minus y. So x is going to contribute plus 1, z is going to contribute plus 1, y will go to minus y, that is it is going to contribute minus 1. So total character for vectors on the oxygen atom is going to be equal to plus 1. Same is going to be the case for these two hydrogen atoms, plus 1 here as well as plus 1 from here. So total character of the matrix for sigma v x z symmetry operation is going to be equal to plus 1, plus 3, sorry. So then if we do sigma v y z, now the two hydrogen atoms change position, and that is why they do not contribute towards the character. And when we do reflection on sigma v y z, the y coordinate and as well as the z coordinate do not change direction, while x coordinate will go to minus x, and that is why plus 1 from y, plus 1 from z, minus 1 from x, and the total character of the matrix is going to be equal to plus 1. So this is the reducible representation that we obtained by taking all the three all the degrees of freedom of water molecule as the basis. Now what we can do is we can find out how many times each of these irreducible representation appear in gamma 3n. So that we can do by using the formula that we have derived for finding out the number of times a particular irreducible representation appear in a reducible representation. That is, we need to take 1 by h, then chi r, that is for the reducible character of a symmetry operation in the reducible representation, and character of the same operation in the irreducible representation when we multiply, and when we sum it up for all the symmetry operations present within that particular group, then this is going to give us the number of times the irreducible representation A, say I, gamma I appears in the reducible representation here. So if we write this, if we do this exercise and find out how many times A1 appears in gamma 3n, so A1 we will find out 1 by h is equal to 4 here, because there are 4 symmetry operations. The order of the group, that is C2P point group, is equal to 4. Then we take the irreducible representation, character of the identity operation in the irreducible representation, as well as in case of the reducible representation, and then we multiply these two. Then we continue doing this for all the symmetry operations. So we move to the C2 symmetry operation, character of the irreducible representation, and character of C2 in the reducible representation. Then sum it up with the character of the sigma v except symmetry operation in the irreducible representation with the character of sigma v except in the reducible representation. Then we do it for sigma v yz as well, and this is what we get. So this will give us 1 by 4, 9 minus 1 minus 1 plus 3 plus 1. So that is going to be equal to 12 by 4. So answer is going to be equal to 3. So what it tells us is that the A1 irreducible representation appeared 3 times in this reducible representation gamma 3 1. So we can write that this is equal to 3 A1 plus. We will need to find out how many times the other irreducible representation appeared in gamma 3 1 as well. So let's do this for A2 1 by 4. Once again we have to do 1 into 9 plus 1 into minus 1 plus minus 1 into 3 plus minus 1 into 1. So this is going to be equal to 9 minus 1 minus 3 minus 1. So that is going to be equal to, because this is going to be minus 5. So this is 4 by 4. 9 minus 5, 4 by 4. So answer is going to be equal to 1. So A2 irreducible representation appear one time in this reducible representation, and we can write again here that A2 appears one time in this gamma 3n. So similarly, if we now do that for B1 as well as B2 irreducible representation, plus 1 this becomes plus 3 minus 1. So this is again 12 by 4, 3. So B1 also appears 3 times in this irreducible representation, in reducible representation. And we need to now find out how many times B2 appears in this reducible representation. Nine minus plus 1 minus 3 plus 1. So that is going to be equal to 8 by 4. Answer is equal to 2. So B2 irreducible representation appears 2 times in this reducible representation. 2 B2. So now we can also verify, or we should check whether the answer is correct or not, because we know gamma 3n is a 9-dimensional irreducible representation and all reducible representation, and only irreducible representation here A1, A2, B1, B2 are 1-dimensional representation. So we need 9 of such 1-dimensional representation to build a 9-dimensional reducible representation, and we should see if there are total 9 irreducible representations present in this case or not. So that is 3A1 plus A2, 4 irreducible representation plus 3, that is 7 irreducible representations plus 2. So total 9 irreducible, one-dimensional irreducible representations are actually present within this reducible representation, and that is why we can now be sure that our calculation is correct. So then we have found out the components or the irreducible components of this reducible representation gamma 3, and now some of these irreducible components representations belong to the three of these irreducible representations actually belong to the translational modes, and three of them also belong to the rotational modes, and the rest belong to the vibrational modes. So we should separate these irreducible representations to find out, that is, we should deduct the irreducible representations for the translational modes as well as the rotational modes, and then we will get the irreducible representations for the vibrational modes of symmetry. So we can do that this exercise by two different approaches, and we will illustrate both these approaches over here. So let us first write the reducible representation that we will get by taking the translational modes as the basis. So we have already done this in the earlier lectures, how to find out the reducible representation by taking the translational modes of symmetry as the basis. We can do that by simply taking the three-dimensional Cartesian coordinate on the central atom as the basis, that is translation along x, y, and z as the basis, and then we will get these gamma t. But if you are lazy, then if you do not want to do that exercise again, what we can do is that we can just look at the character table and then write the symmetry of the translational modes, that is the irreducible components of the reducible representation if you take the translation mode as the basis, as well as we can write the character of this reducible representation, that is gamma t, by looking at the character table itself. So we know that the translation along x has b1 symmetry, translation along y has b2 symmetry, and translation along z has a1 symmetry. So we know that translation, if we take gamma t and reduce it into its irreducible components, we will get answer equal to a1 plus b1 plus b2, because a1, the z-axis transforms, translation along z transforms as a1, translation along x transforms as b1, and translation along y transforms as b2, and that is why the reducible representation that we are going to get by taking the translational modes as the symmetry, if we find out the irreducible components, we will get this as the answer, and this we could find out by simply looking at the character table itself. So how can we find out the character of these gamma t? By looking at the character table. That is, you can just add up the characters of a1, b1, and b2 for different symmetry operations, and that is going to be equal to the characters of this reducible representation gamma t. So if we add the characters of a1, b1, and b2, that is 1 plus 1 plus 1. This answer for identity operation is going to be 3. This is a three-dimensional representation because we have three coordinates x, y, and z here. So character of identity operation is going to be equal to plus 3. So then if we take for C2 operation, plus 1, minus 1, minus 1. So this is going to be equal to minus 1. If we add these three characters, then we will get answer equal to minus 1. And then sigma b xz, 1 plus 1, that is 2, minus 1, that is going to be equal to plus 1. And then for sigma b yz, 1 minus 1, that is 0, plus 1. So this is going to be also going to be equal to plus 1. So we now also have the characters of the reducible representation by taking the translational modes as the basis, and we can build these characters, or we can find out the character of this reducible representation just by looking at the character table. We don't have to work it out ourselves. So then, if you take this reducible representation and find out its irreducible components by using the formula that we have used for finding the irreducible components of say gamma 3n here, you will find the answer equal to a1 plus b2, b1 plus b2, and you should do this exercise to verify whether it is correct or not. So then what we will do is that we will also write the characters of the rotational modes that if we character of the reducible representation if we take that we obtain if we take the rotational modes as the basis, that is gamma r, and we can find out the characters of gamma r as well as the irreducible components of gamma r again by looking at the character table, because we know that Rx transforms as B2, Ry transforms as B1, and Rz transforms as A2. So that is why the irreducible components of this reducible representation gamma R is equal to A2 plus B1 plus B2. So that we can write just by looking at the character table itself. And again, the way we did it for gamma t, we can find out the characters of gamma r as well. So we need to add the characters of these three irreducible representations to get the character of gamma r here. So that is going to be equal to -1 here, -1 here, and -1 out here. So these are the characters of gamma r, and these are the irreducible components of gamma r. So again, you should take these characters of this reducible representation gamma r, and you should find out how many times these irreducible representations appear in gamma r, and you should find answers equal to this, that a1 does not appear, that is you will find a small a1. In case of gamma r, you will find the answer to be equal to 0, while for a2, b1 and b2 you will find answer equal to 1, 1 and 1. So all these three irreducible representations appear one time, while a1 irreducible representation appear on 0 times in this gamma r. So now we have the characters of gamma r, gamma t as well as gamma 3n. And now to find out the characters of gamma vibrational, that is the character of the reducible representation, when we take the vibrational mode as the basis, that we can do gamma vibrational is nothing but gamma 3n minus gamma t gamma r. So if you take the characters of gamma t and gamma r and deduct them from gamma 3n, then we will get the character of gamma vibrational. The same can be applied here as well. We can take the irreducible components of gamma 3n and then deduct the irreducible components of gamma 3 and gamma r, and then we will see the irreducible components of gamma vibrational. So we can do this exercise here. Let us proceed with that. So gamma vibrational, take the character of gamma 3n and deduct the characters of gamma t and gamma r. So 9 minus 3, again minus 3, 9 minus 3 is going to be equal to plus 6, minus 3 is going to be equal to plus 3. So minus 1 minus minus 1 is going to be equal to, then this is going to become plus 1, so this is going to be equal to 0, and then minus 1 is going to be there, so this is going to be equal to plus 1. Then 3 minus 1, that is going to be equal to 2, minus 1 is going to be equal to, this is going to become plus 1, so 2 plus 1 is going to be equal to 3, and then 1 minus 1 is going to be equal to 0, but minus 1 is going to be equal to plus 1. So these are the characters of the reducible representation if we take the vibrational mode as the basis. We do not know what are the vibrational modes in case of the water molecule, but even without knowing the exact vibrational modes in water molecule, we can figure out the characters of the reducible representation that we are going to get if we take the vibrational mode as the basis. This for the water molecule, we can figure out the different vibrational modes because it is a small molecule, but for large molecules it is going to be difficult for us to figure out the vibrational modes just by looking at the molecule itself. So this essentially allows us to work out the character of the reducible representation. If we take the vibrational mode of symmetry of a say large molecule also as the basis. So now we have the characters of gamma vibrational, reducible representation gamma vibrational, and we can take these characters and then find out how many times these irreducible representation appeared in gamma vibrational. So let us do that. Let us find out how many times these irreducible representations appear in C2B point group appear in gamma vibrational. So let's do A1. So that is going to be equal to 1 by 4, 1 into 3, it's 1 into 1, 1 into 3, 1 into 1. Into 3. So this is going to be equal to 3 plus 3 plus 2. So this is going to be equal to 8 by 4. So 2. So A1 appears 2 times in this reducible representation gamma vibrational. Let's write here that A1 appears 2 times. So let's write here 2 A1. So then let's also find out how many times A2 appear in gamma vibrational. So 1 into 3 plus 1 into 1. So then minus 1 into 3 plus minus 1 into 1. Minus 1 into 1. So this is going to be equal to this plus 3 and minus 3 will get cancelled, plus 1 and minus 1 will get cancelled, so we have 0. So the total answer is going to be equal to 0. So then that means that A2 irreducible representation does not appear in this reducible representation gamma vibration. So none of the 3 vibrational mode in water molecule have A2 symmetry. That's what we can say. So then minus 1 into plus 1 plus 1 into 3, 1 into 3 plus minus 1 into 1, minus 1 into 1. So that is going to be equal to this plus 3 plus 3 plus 6 minus 2. So that is going to be equal to plus 4, and this answer is going to be equal to 1. So B1 irreducible representation appear 1 time. So we can write here that one of the vibrational mode of symmetry has B1 symmetry. Now itself, because the gamma vibrational is a 3-dimensional reducible representation, and we have found out that the irreducible components that A1 vibrational A1, and then there are 2 A1 modes while there is 1 B1 mode. So we have already found the symmetry of all the 3 vibrational modes, and now if we do AB2, we know that the answer should be equal to 0, because if it is equal to 1 or 2, then the number of the one-dimensional representations is going to become more, and that cannot be true because only 3 one-dimensional irreducible representations can be part of this 3-dimensional reducible representation. So we will anyway do this and then find out whether the answer is going to be equal to 0 or not. Minus 1 into 1 plus minus 1 into 3 plus 1 into 1. So we see that this is plus 3, this is minus 3, minus 1, minus plus 1. So answer is going to be equal to 0. And B2 irreducible representation does not appear in this reducible representation gamma vibrational. So we have found out the symmetry of all the three vibrational modes. Two of the vibrational modes have A1 symmetry, or we can say two of the vibrational modes are symmetric vibrational modes, and one of the vibrational mode has B1 symmetry. So this is one of the approach through which we can find out the symmetry of the vibrational modes. Then we have an alternative approach as well to find out the symmetry of the vibrational modes, because we already know the irreducible components of the gamma 3n, as well as we know the irreducible components of gamma t and gamma r. So if we take the irreducible components of gamma 3n, and then if we deduct the irreducible components of gamma t and gamma r from gamma 3n, again we should get the irreducible components of gamma vibrational, and we should see, or we should get the answer equal to 2a1 plus b1 if we deduct these irreducible representations from over here. So let us do that and let's see if it is correct or not. So a1 appears 3 times in gamma 3n, while if you see a1 appears 1 time in gamma t and it does not appear in case of gamma r. So if we deduct a1, 3a1 minus a1, so it is going to be 2a1 plus, so a2 appears 1 time in gamma 3n, and here it does not appear, while here it appears 1 time. So a2 will get cancelled out completely. 3b1 minus b1 minus another b1 over here, so there is going to be, we are going to be left with 1b1 over here, 2b2 minus b2 minus b2, so b2 again will get completely cancelled out, and b2 will not appear in case of the gamma vibrational. So what we have seen over here, that again we get answer equal to 2a1 plus b1. Again we see that two of the vibrational mode are of a1 symmetry, and one of the vibrational mode has b1 symmetry, or if you take the two of the vibrational mode as the basis, they will transform as a1, while one of the vibrational mode will essentially form the basis for b1 irreducible representation. So the answers do match if we take the characters and then find out the irreducible components, or if we take the irreducible components of gamma 3 and gamma t and gamma r, again we get answer equal to 2a1 plus b1. So this essentially brings us to the end of this lecture. What we have learned during this lecture is that we have learned how to find out the symmetry of the vibrational modes in a particular molecule by just looking at the character table of that molecule, and then by figuring out the reducible representation, that is gamma 3n. Once we have the characters of gamma 3n, we can take the characters of gamma 3n and deduct the characters of gamma t and gamma r to get the characters of the reducible representation gamma vibrational, or the reducible representation that we obtained by taking the vibrational modes of symmetry as the basis. Now we can take these characters and then find out the irreducible, how many times the irreducible representations in that point group appear in this reducible representation, and this gives us that in case of water molecule, the answer comes out to be 2a1 plus b1, or it tells us that two of the vibrational modes in water molecule has a1 symmetry, while one of the vibrational mode has b1 symmetry, while none of the vibrational mode in water molecule has a2 or b2 symmetry. Then we have another approach to find out the symmetry of these vibrational modes, that we can take the irreducible components of this irreducible representation gamma 3n, and from there we can deduct the irreducible components of this gamma t and gamma r, and that will essentially give us again the irreducible components of this vibrational the reducible representation that we obtained by taking the vibrational mode as the basis, and that essentially tells us the symmetry of different vibrational modes in a given molecule.
So let me conclude this lecture with this. During this next lecture, we will learn how to find out or how to deduce how if these vibrational modes are IR active or Raman active, or even to say figure out the whether a given electronic transition is going to be symmetry allowed or symmetry forbidden by just doing a few calculations or by having a look at the character table and then doing a few calculations, very easy calculations, will allow us to predict all these important or answer all these important questions. So till then, let me thank you for being with me during this lecture, and uh, I'll see you during the next lecture. Thank you very much.